Now, in this episode, we shall solve some examples on reflexive, symmetric, and transitive relations. Example 1. Show that the relation R on the set A, where set A is equal to 1 to 3, given by R is equal to 1 1 2 2 3 3 1 2 and 2 3, is reflexive but neither symmetric nor transitive. Now let's first check whether this relation is reflexive or not. Now a relation is reflexive if every element in it is related to itself. Let's see. Now it has got three elements, 1, 2, 3. Now let's see whether 1 is related to 1. So it's related. 2 is also related to 2. And 3, 3. 3, 3 is also related to 3. That means this is a reflexive relation. Now let's check whether this relation is also symmetric. Now this relation will be symmetric if AB is related, then that means BA is also related. Let's check each element. Now we have first 1 1. 1 1 is related, and when we interchange the position, we have 1 1 again 1 1. So it is still related. On 2 2. 2 2 is also related when we change the because the elements are same. 3 3 is also related, that it will, if we change the position, still it will remain related. 1 2. Now if we change the position of 1 and 2, then it will become 2 1. Now 2 1 is not a part of this relation, and similarly 2 3, when we change it, it becomes 3 2, and 3 2 is not a part of this relation. So this relation is not symmetric. Now let's check whether this relation is transitive. Now remember, a relation is transitive if AB is related and BC is related, then that also means AC is also related. Now here you can see, let's see which pair we can check for transitivity. The last one. Here we got 1 2 is related and 2 3 is also related. Now this relation will be transitive if 1 3 is also related. But you can see 1 3 is not a part of this relation. We don't have any pair 1 3 which exist in this relation. That means this relation is not transitive. So this relation is reflexive but neither symmetric nor transitive. Let's solve one more example. Check the following relation R and S for reflexivity, symmetry, and transitivity. A or B. A is related to B if and only B is divisible by A, for all A and B belong to natural numbers. Now this relation will be reflexive if A is divisible by A. We know every number which is natural number is always divisible by itself, because when we divide a number, natural number by natural number, then the result is 1. That means A is related to A for all A which belong to natural number. So that means R is reflexive on N. Now let's check it for symmetric, whether this relation is symmetric or not. Now this relation will be symmetric if A is related to B, then that also means B is related to A. Now take an example. Suppose we say 6 is divisible by 2. Now 6 is divisible by 2, that means 6 divided by 2 is equal to 3. But now is 2 is also divisible by 6. Now 2 by 6 is equal to 1 upon 3. So 2 is not divisible by 6. That means this relation is not symmetric. Now let's check whether this relation is transitive or not. Now suppose ABC belongs to natural number and A is related to B and B is related to C. Now if A is related to B, then that means B is divisible by A. That means B upon A is equal to a natural number M. And also B is related to C. That means C is divisible by B, or C is equal to B into n. Now B is equal to M into A and C is equal to N into B. Or we can say C is equal to N into B, or C is equal to N into MA, or C is equal to Mn into A. Now M and N are natural numbers, so Mn is also natural number. That means C is equal to Mn into A, or C is also divisible by A. That means A is also related to C. Now A related to B and B is related to C, then A is also related to C. So that means this is a transitive relation. So this relation is reflexive and transitive. So this relation is reflexive and transitive, but this is not a symmetric relation. Example 3. Let S be the set of all points in a plane and R be a relation on S defined as R is equal to the set of all P and Q such that distance between P and Q is less than 2 units. Now show that R is reflexive and symmetric but not transitive. Now let's first check it for reflexivity. Now take any point P in set S in the given plane. Now we can see that the distance between P and P is 0. That is, the distance between the point and the point is always 0, which is less than 2 units. So that means P and P belong to given relation. So P and P belongs to R for all P which belongs to given set S. So R is reflexive on S. Now let's check whether this relation is symmetric. And now let P and Q be 2 points in S, that is a given plane S, such that P and Q belongs to R. That is, P and Q belongs to relation R. Now P and Q belongs to R, that means distance between P and Q is less than 2 units. Now P and Q are 2 points and the distance between P and Q is less than 2 units. We can also say distance between Q and P is also less than 2 units because the points are same. But if the distance between Q and P is less than 2 units, then that also means Q and P also belongs to R. Now P and Q belongs to R and Q and P belongs to R. So that means the given relation R is symmetric on S. Now let's check whether this relation is also transitive or not. Now suppose we have got 3 points P, Q and R on the given set S. And now suppose P and Q belongs to R. That is, the distance between P and Q is less than 2 units. Now suppose the distance between P and Q is 1 unit and we have them on the same plane, P and Q. You can see the 2 points. The distance between them is 1 unit. Now suppose Q and R also belong to R. That means the distance between Q and R is also less than 2 units. Now let's again assume the distance is say 1.5 unit. Now the distance between P and Q is 1.5 unit and the distance between Q and R is 1.5 unit. And now if I ask you what's the distance between P and R, so you can see 1 plus 1.5, it is 2.5, but that is not less than 2 unit. So that means if P and Q belongs to R and Q and R belongs to R, then that doesn't necessarily means that P and R also belongs to R. That means R is not transitive on S.